Hello guys, welcome back to TechDose, and in this video we will look at house robber 4 problem, which is from Leetcode number 2560. Good problems to solve. After having solved this is maximum candies allocated to K children problem from Leetcode number 2226, and minimized maximum of products distributed to any store from 2064. I have already explained both these videos in detail, so you will find the links in the description below. You can go ahead and check it out after solving this problem. In this problem, there are several consecutive houses along a street, each of which has some money inside. There is also a robber who wants to steal money from the homes, but he refuses to steal from adjacent homes. The capability of the robber is the maximum amount of money he steals from one house of all the houses he robbed. You are given an integer array nums representing how much money is stashed in each house. More formally, ith house from the left has nums I dollars. You are also given an integer k representing the minimum number of houses the robber will steal from. It is always possible to steal at least k houses. Now this is an important point. Return the minimum capability of the robber out of all the possible ways to steal at least k houses. So if you look at the first example, here we have 4 houses and the k value is 2. Now in how many ways can the robber actually steal from any of these houses? So if you consider all these values which are given, then the robber can either try not to steal from a house or steal from that house, right? Now if he do not steal from the house, he can go to just the adjacent house which is at 3, and he can again choose one of the two options, right? So each of the houses will have one of the two options. But if the robber actually takes a decision to steal at 2, he will have to skip the adjacent house and go to the I plus 2th house, right? Just by skipping the next adjacent house. In either case, if you generate all the possible combinations in which the stealing can happen, it will be approximately 2 to the power of n, because every houses have 2 choices, right? And if there are n number of houses, you will have order of 2 to the power n combination. Yes, you can generate all these combinations by using recursion, and you can optimize this by using dynamic programming, and the time complexity will be approximately order of n square. But we are not solving it using dynamic programming, and the reason is, if you look at the constraint, it is showing about the nums length being 10 to the power of 5. So if you write an n square dp approach, then it will be 10 to the power of 10, which is greater than 10 to the power of 8, and that is why this will give you a TLE. So if the dynamic programming solution is giving you TLE, this means that there must be a greedy approach to this, or otherwise a more optimized DP solution, right? In this case, we have a greedy solution to this. This is how you identify and don't overkill the problem by just using dynamic programming. Okay. Now each of the numbers are within the 32-bit integer range, and the k value is always less than equals to half of the items. Fine. Now once we have seen this, let's look at some observations which will help us solving the problem optimally. In this case, let's assume we have 6 items and the k value is 2. According to the constraint, it was given that k will be less than equals to half of the array items. Since the problem guarantees it is always possible to pick k non-adjacent houses, therefore we will always exactly pick k houses, because we cannot pick less houses, right? And why do we pick only k houses? Because let's say that our capability k value is equals to 2, and since our goal is to minimize the maximum across all the combination of k picks, let's say that one of the combination that I picked was 2, 1, because I was forced to pick at least k items. Now if you are giving me a counter argument that why don't we pick more than k items, you can try picking any other item after 2 and 1, and you will always get into trouble. Like even if you had more items, let's say 4 here at index 6, and according to the condition you can pick 4. So why will you pick this 4? Because the capability of this entire combination will increase. The capability is equals to the maximum of everything that you have picked. That means the houses that you have stolen from, the maximum of that house will be taken as the capability of that combination. So ask yourself, if you have the luxury of picking less items as compared to picking more items, which one will be giving you the minimum result. It will always be the one where you have to pick less items, right? Okay, so it will always be optimal. The minimum value that you get by picking less items will always be less than equals to the minimum value that you get by picking more items. So I will never ever try to pick more than k items, fine, because our goal is to minimize the capability over all the combination of picks, right? So stealing from more than k houses is never sensible. You can just think about it, it will be very logical. Now let's try to do problem deduction. In this case I am assuming 7 items and the k value being 3. Now if I have to pick 3 items out of these 7 items, according to the rule that no 2 adjacent items can be picked, then what will be the minimum that I can pick? Well, the minimum can be 1. Okay, maybe in this array, maybe all the items were 1. All the items were 1, right? So if you pick 3 items and take the maximum value of that combination, the maximum value can be the minimum of the entire array, right? So that is what I am talking about. So in this case, if you pick k items, in the worst case you can end up with the minimum value. You can say it is the best case as well. You can end up with the minimum value, which is 1, right? So if you choose a combination with the k items, k equals to 3, you have picked 3 items, then out of these 3 items, the maximum of the 3 items can be the minimum of the entire array itself. Okay, lower than that will never be possible. So that is how the minimum possible capability, that the answer that you can generate as the result of this entire problem solving will never be less than the minimum of the array. And with the same reasoning, the maximum possible capability that you can get according to the problem statement can never be more than the maximum of the entire array, right? So by just looking at the array, you are sure what is the minimum answer and what is the maximum answer. Maybe 1 may not be the result, maybe 7 may not be the result, but this is the range in which your answer must lie. Okay, because if you are going to steal, the values will always be within the range of minimum to maximum. It is not going to go anywhere else, right? So I have determined the range of my answer from 1 to 7. Now according to the problem, we have to pick k houses and try out all possible combination of k houses and keep taking the maximum of each of the combination, try to minimize it. Like, let me give you 2 such picks. Now if k is equals to 3, I can pick 2, I can pick 6, I can pick, let's say, 3. If I pick this as one of the combination, then what is the maximum across this pick? It is 6. So in this combination, the capability which is coming is 6. If I pick another combination, like let's say I had picked this 2, I had picked this 1, and I had picked 5. Okay, so if you pick 2, 1, 5, what is the capability that you are getting? Capability that you are getting is the max of 2, 1, 5, which is 5. If I pick 5, 1, 5, the capability we get is again equals to 5, right? So out of all the k type combinations, like you will have many more combinations. I am not going ahead with that. Out of all these combinations, whichever one is the minimum capacity that you are getting, that will be the result, isn't it? So in this case 5 will be the answer. In this case 5 will be the answer. You can just try it out. So if 5 is the result, then is it lying between our answer range from 1 to 7? Yes, it is lying. And how do I know that? Because I know that the answer cannot be less than the minimum and cannot be more than the maximum. It has to be one of the array element only. Fine. Now if I ask you the question that can you pick k items where the capability is less than equals to 6? Well, I have already picked k items where the capability is exactly equals to 5. So can I pick the same combination? Like, can I pick this 5, 1 and 5 and say that I have picked a combination where the capability is less than equals to 6? Yes, it is always possible. And for the same reason, any higher value, like let's say, can you pick a k combination in such a way that the capability is less than equals to 7? Yes, you can return the same combination again. But if I tell you that can you pick a k combination from here where the capability is less than equals to 4, let's say, Well, that will not be possible, because the minimum that we could manage was 5. So any value less than 5 will not be possible, 4 will not be possible, 3 will not be possible, and so on. So if I know that the answer will lie in the range of 1 to 7, and if I know that if I have to pick k items from this array according to non-adjacent selection condition, and I got the minimum capability to be 5, then anything lower than 5 is not going to work for me, and everything from 5 and beyond that point will always work for me, because you can always return the same combination for them, right? 5, 1 and 5. Okay, so this problem can be said to be the problem of crosses and ticks, where from the beginning maybe 0 or more values may not work, but when certain value has started working, everything after that will work. Okay, now if I give you this question, let's say this is the given array, can you find out what is the first tick? If you try to find what is the first tick, then you can easily do it by linear search, by just going from left to right, and whenever you see the first tick, you just return the index of it. That is one way to do it. But you can do better, since you know that all the crosses are on one side and all the ticks are on the other side. You can easily do it with binary search, because you can just apply a low here and a high at the end, and you can calculate the mid value. Now if you try to pick key houses from this given array, and if the capability cannot be less than equals to 4, that means this is not working for us. And if 4 is not working for us, I already know that none of the lower values will work for us. So let's go to a higher value. So L will be made to mid plus 1, and then again you will have 6 as the mid. Now if you can actually pick key houses from this array where the maximum capability is less than equals to 6, then 6 will work for us, and everything larger than this will always work for us. So you can save this in your answer and say that 6 is the answer. And so you will be searching on the left side now and make high equals to mid minus 1. Now in this case again, your mid value is equals to this 5, and if we can find another assignment of key houses according to non-adjacent selection, then 5 is also working for us, and everything larger than 5 will work for us. So save this in your answer 5 and go to the left side. So when the high becomes less than low, that is where you stop, and the answer will be keeping a track of what is the lowest index for the tick mark. This is how you solve the crosses and tick. If you want to solve an easy version of this problem, then that problem is the first bad version from Leetcode. First bad version. I have already made a video on this. This problem is based on the first bad version. You just have to do the problem deduction. Okay. Now I think it is clear why we will be applying binary search, and we will be applying binary search not directly on the array itself, but we will be applying it on the range of answer, and the range of answer will always be from the minimum item of the array to the maximum item of the array, and you can say that it is the range, which is max minus min. And we know that the range will be 10 to the power 9 minus 1, right? It was already mentioned in the problem. Now having understood that we will be applying binary search, let's now try to understand how to pick k number of items from the given array according to the condition of non-adjacent selection. Now let's say that I want to find key houses in such a way that the capability should be less than equals to the given value 6. Okay, I want to do that. So how to do it? I mean, definitely we cannot actually create all possible combination which will be 2 to the power of k or 2 to the power of n. That I do not want to do. So simply what I will do is, whenever I move from left to right, whenever I see an item here 5, then I can actually choose whether it has to be included if it will satisfy the given value. That means if this given value is less than equals to 6, then I can include it. But if you ask me, how do you know that whether we will be including it or not, maybe not including it will give me a better result. Well, to counter your thought process, let's look at a proof. Let's say that you are looking at 5, and let's say that you want to maintain the capability less than equals to 6. Your dilemma is whether I should pick this 5 or not pick this 5. Let's say that the next three items are A, B and C. All these items can be less than equals to the value, or all these items can be greater than value, or some of them can be less and some of them can be greater. Let's consider the best case scenario where I say that all these items A, B, C are actually less than equals to value. So if I happen to pick this 5, I don't care how many items are on the left and right. If I pick this 5, I can easily choose one of these two options, B and C. If any one of the B and C is actually less than equals to value, then the number of picks out of these 4 items which is satisfying our capability condition will be 2 picks. But let's say that you do not pick this 5 even after knowing that 5 is actually following the condition. And let's say that okay, you said okay, I will pick A because A is less than equals to value, so you have picked this one. Okay, so this is your first pick. Even after this first pick, you just have an option with C. If C is less than equals to value, then only you can pick C and say that my length will be 2 picks. I actually made 2 picks. But if C is less than equals to value, then why don't I pick this 5 and actually guarantee that these 2 picks will actually be optimal? Why don't I do that? Now, if you skip this 5, there can be a case that if B is actually less than equals to 6, but C is not less than equals to 6, then your length will end up being only 1, where you just picked A and C was greater than the value, so you will get a wrong answer, right? So according to this, it is always optimal that whenever you see a value, whenever you see an item having a value less than equals to whatever capability you are trying to look at, like I want to select k number of houses where the maximum of the pick is less than equals to value, I will always select 5. It will always be optimal. You just try it out. Okay, it will always be optimal. It does not matter whether A, B, C are greater than value, less than equals to value, or some of them are greater, some of them are smaller. You will never be able to maximize the length if you do not pick this 5. Okay, either the length will be same or it will be lower. So if 5 is less than equals to value, then always include 5. Even if A, B, C are all less than equals to the given value, still you cannot pick more than 2 items by not picking 5. And this is your greedy strategy. And if you understand this greedy strategy, then you will confidently be able to select key items in just O n time by parsing it exactly one time. Now let's see how to do that. So if the capability that I'm trying to solve is for 6, like I want, in the previous approach when I said what is the mid value, whenever you pick a mid value, I want to select key items from the given array and do non-adjacent selection in such a way that the maximum of that selection is less than equals to the mid value. Okay, so let's say this is your given mid value, which is 6. So I want to select key items, 3 items from this entire array in such a way that the maximum of that selection is less than equals to 6. According to this proof which we have seen, if I see a 5, I will include that. So you can keep a counter to just count how many items I have selected, right? So this will tell you if at the end the count value is greater than equals to k, then you can simply return true, saying that we can actually select key items with maximum capability less than equals to 6. Let's see this. If you see a 5, then you increment the counter, but then you cannot go to the next item. You have to skip this item and go to the index number 2. 7 is not less than equals to 6, so you just go to the adjacent item. 6 is less than equals to 6, so you select one more item. Now you jump across 4 and reach to 5. 3 is less than equals to 6, so yes, you can include one more item. You jump across and reach to index 7. You have gone out of bounds, so you will stop. Now since you could select at least 3 items, like key items, right? So if count is greater than equals to k, then we need to return true. That means we can select at least k items from this given array where the capability was less than equals to 6. So if 6 works for us, then I will try with the smaller values, right? So this is the entire idea behind the greedy pick. Now once you have understood which algorithm we are applying, that is binary search, and how to actually apply the greedy pick for any mid value, then let's see the dry run using the binary search plus the greedy pick. So in this case, given the array having 7 items and the k value being 3, my lowest possible answer can be 1, which is the minimum of the array, and the highest possible answer can be 7, which is the maximum of the array. The mid value will be calculated as low plus high minus low by 2 to avoid any possible chance of overflow. Now let's try to proceed. In this case, the mid will be 1 plus 7 minus 1 by 2, which will be 4. So now I have to try with an assignment of 4. Can I pick 3 items minimum from this array where the capability value is less than equals to 4? Let's try this out. If I see a 5, can I pick it? No. The counter will start from 0. If I see a 2, can I pick it? Yes. Counter will become 1 and you jump across to index 3, skipping the index 2. If you see this 6, can you pick it? No. If you look at this 1, can you pick it? Yes. So you jump across to index 6. Now can you pick this 5? No, because it is greater than 4. So after that you go out of bound, and once you are done with this, check the count value with the k value. So since count is less than k, that means we could not actually select k items. So our capability less than equals to 4 by selecting k items is not possible. We were not able to select k items. So this is not working for us. So if 4 is not working, you know where to go. You have to search on the right hand side. So the low value will become 5 and the high value will remain same. And similarly, you can imagine that the mid value will be coming to be 6. So let's see if we can select k items by maintaining the capability less than equals to 6. Again, the counter will restart at 0. You will start back at this index 0. Can we select this 5? Yes. 5 is less than equals to 6. You can select it and the count will be 1. You jump across to this 7. Can you select 7? No. It is actually greater than 6. So you go to this 6. Can you select it? Yes. 6 is less than equals to 6. Select it. Jump across and reach to 3. Can you select it? Yes. 3 is less than equals to 6. So the counter value becomes 3. Since it is working for us, I will save it in my result and I will search on the left hand side, because all the higher values will definitely work. So my high value will become mid minus 1, which is 5. Low was already 5, high is 5. So the mid value will now be 5. Now let's try for the value 5. Again, you have to start from index 0. Again, the counter will be made as 0. 5 is less than equals to 5. Increment the counter, reach to this index 2. 7 is it less than equals to 5? No. Go to the next item. 6. 6 is not less than equals to 5. Go to 1. 1 is less than equals to 5. Increment the counter, jump across to 5. 5 is less than equals to 5. So increment the counter and jump across to 8. So this is out of bound. Now you check if count is greater than equals to k. Yes. And that is why 5 is also working. So overwrite this value to 5. And you go on the left side. If you go on the left side, the the high will be mid minus 1, which will be 4. And since high is less than low, that is where you have to stop, and whatever is stored in the result is your answer, which is 5. Okay. So this is how you calculate the minimum capability across all the maximums, right? So it is kind of a mini-max binary search. Now, if you consider about the time complexity, it will be log of r, because you are applying binary search on a range, and the r is actually the maximum minus the minimum item. And for every mid value, you have to go across the entire array to check if you can actually pick k number of items, right? So that makes it n log r. So the time complexity is n log r. Space complexity is order of 1. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. Now this code is self-explanatory, where we are given the nums array and the value k. I will be finding the minimum element of the array and store it in low, maximum element of the array, store it in high, and take the mid variable. Then I will be taking an answer and do binary search on the answer range. So I will be finding the mid value and I will check if I can pick k number of items with the capability value less than equals to mid from the nums array. So if you check the can assign function, it is the greedy pick algorithm where I will be keeping a counter equals to 0, iterate across all the items. This is incrementing I by 1 time, and if the num size is less than equals to max value, then increment the counter and I will increment I again at this point, so that I is incremented 2 times if you happen to pick an item. Here is the first increment and here is the default incrementer, right? After the for loop, after doing the assignment, if you can pick greater than equals to k items, that means you return true, otherwise you return false. So if you can assign, then save the value in the answer and move to the left hand side by doing high equals mid minus 1. Otherwise, if the mid value did not work, then we have to go on the right hand side and do low equals to mid plus 1. Once your binary search is over, the answer will be storing the final minimum capability value that you can assign, so that you can pick k number of items from the given array. So this problem already mentions that the answer exists, therefore I can simply return the answer without any check. So I hope this is clear, and if you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.